Hello everyone, welcome to the Information and Network Security lecture series. This is lecture number 7, and in this particular session we'll study this topics. The first one is the history of DES, that is the data encryption standard, then the flaws in DS which were pointed out by the critics, then structure of the DES, then structure of each round in the DES process, then analysis of DES and weaknesses in DES. So we'll study this topic one by one. So let us first study the history of DES, that is the data encryption standard. Okay. So DES was adopted in 1977 by NEST, okay, and it was designed as a block cipher. And we know what is the meaning of a block cipher. We did it in the last session. DES was a refined version of Lucifer algorithm. Now this Lucifer algorithm was developed by IBM and was commercially available. So this DES became a standard, but this did not become a standard. So this was adopted, DES. There were some flaws in the DES as pointed out by the critics. The first flaw was the size of the key which was used in DES. So DES, it used a key of size 56 bits, although the Lucifer, it used a key of 128 bit, and this was extremely less as compared to Lucifer. So the size of the key was a big problem. It was 56 bits, and we know that to make a secure cryptographic algorithm we need a key of at least 64 bits, and this was less than that. So it was that it won't provide much security. Then the second flaw, as pointed out by the critics, was that the internal structure of DES was hidden. So the critics, they argued that those who are designing DES, they may have left some backdoor, so that anyone who is using DES, then his or her information would be it would be snatched illegally by the one who are designing DES. So these were some of the flaws as pointed out by the critics. Now next is the structure of DES. As we can see, this is the block diagram which shows the structure of DES. On the left side we have, this is the encryption part, and this one, the right, is the decryption part. So encryption part, as we can see, it takes a plain text of 64 bit, therefore it's called as a block cipher. So it takes a plain text of 64 bit, encrypts it, and gets a 64 bit plain cipher text. Okay, we are using the key which is of 56 bit. So the plain text and cipher text are 64 bit, and the key which is used is of 56 bit. So at the decryption side we have input as the cipher text, the same key is used, therefore of course it is called as the symmetric cipher. DES is a symmetric cipher because the same key is used for encryption and same for decryption. So it takes a 64 bit cipher text, it decrypts it, and it returns back the 64 bit plain text. So this is the block diagram of DES. So the input process has input process that of the encryption has two inputs, that is plain text and the key. Okay, and the decryption process has also two inputs and one outputs. The two inputs are of course the cipher text and the key, and output is the plain text. Now let us see the more detailed structure of DES. So this diagram we can see is the structure of DES. Okay, so here we can see input is of course 64 bit plain text. This is a 64 bit plain text. Okay, it is applied to the DES block. The very first process is the initial permutation. So the data 64 bit is initially permuted, okay, and then it goes through 16 rounds. So there you can see there are 16 rounds in DES, round 1, round 2. Okay, the structure of each round is same. Okay, if you see the internal structure, we will see this afterwards, the internal structure. So every round has the same structure. Okay, and for every round we have some sub keys which are applied. So here we have K1, K2 up to K16, and all these sub keys are of 48 bits. Okay, and before the first round there is initial permutation. Output of first round becomes the input of second, output of second becomes the input of third, and so on. It continues until we reach the round 16, and output of 16th round goes to a final permutation. Okay, and of course these two are opposite of each other. That is, if bit number 1 goes to, suppose, bit number 40, then here 40 will go to 1. Okay, so this is the final permutation, and the output of final permutation is the given ciphertext. This is the ciphertext. Okay, then here this we can see the key, the main key is of course of 56 bits. The main key is of 56 bits. This goes through a sub key generation process, and this sub key generation process, it produces 16 different keys, and these keys are called as sub keys, and they are all are of 48 bits. Okay, so this is the what we saw. So let us go point wise. The first point is DES is a symmetric cipher. Why it is symmetric cipher? Because the same key is used for encryption and same key for decryption. Then second thing very important is that it comes under the category of feastal cipher. We saw in the previous session what is the meaning of feastal cipher. So DES comes under the category of the feastal cipher. Then it is a block cipher. So DES is a block cipher because it processes a data of 64 bits at a time. And second, it encrypts and decrypts a block of 64 bits at a time. Okay, the size of the key is 56 bits. Okay, and there are 16 rounds. Okay, all rounds have the same structure. So the plain text undergoes the initial permutation before the first round and undergoes a final permutation after the last, that is the 16th round. Then the 56-bit key, the main key, is applied to a key generator which produces 16 different sub keys. Okay, one for each round, and the size of the sub key is of 48 bits. Okay, now let us see the internal structure of each round. This is the structure of each round. Okay, as we can see, so this is LI RI. Now why we are using this I? Because this I can be from 1 to 16. Okay, so if it is first round, this I is 1, and this KI means the first key. If we are taking the first round, it becomes K1, and this Li plus 1. Why it is Li plus 1? So if this is 1, this becomes 2. If this is 2, it becomes 3, and so on. Okay, now what is done in this case? So it comes under the category of feastal cipher. So in the feastal cipher, as we saw, that the data is first divided into two halves, right half and the left half. So here we have the left half which is of 32 bits, the right half which is of 32 bits. So 64 bit is divided into two parts, 32 right and left half. The right half, it becomes the left half of the next round. It also goes into a function, so we can assume that this right half, we make two copies of this right half. One becomes the left half of the other round, and another copy, it goes through a function, and some key, and the key is applied, that 48-bit sub key actually is applied, and it goes through a function. Okay, some function is applied. Okay, and we get output. Okay, that output is XORed. We do XOR operation with the left half of this, and after whatever output we are getting, it becomes the right half of the next round. So this thing, it goes on for 16 rounds. Okay, it goes through the 16 rounds, and then whatever output we get, that is the ciphertext after the final permutation. So this is the structure of each and every round. Okay, then let us do the analysis of DES. So there are two desired properties of block cipher. One, it should have an avalanche effect. The second, it should have the completeness property. Let us see whether DES is satisfying this or not. The first one is the avalanche effect. Now avalanche effect means that a small change in the plain text or the key must create a large change in the ciphertext. So if we analyze this, we can see that DES satisfies this strongly. So suppose if we have some plain text message of 64-bit, and suppose we get the ciphertext. Okay, now even if we make a change in a single bit, okay, if we change a single bit out of all these 64-bit, only single bit is changed, then there is a large change in the ciphertext. Many bits of the ciphertext get changed, so because of only single change. So this is called as avalanche effect, and DES satisfies this strongly. Then regarding the completeness effect, so completeness effect means that every bit of ciphertext needs to depend on many plain text bits. Okay, so what does it mean? That suppose if we have 64-bit ciphertext, let us take the leftmost bit. So this leftmost bit, whatever we got, it is the result of many operations on the 64 bits plain text. Okay, so this bit is result of only one bit of plain text, but many number of, or you can say almost all the bits in the plain text. Okay, so this is satisfied strongly by DES using diffusion and confusion. So these two properties which are desired in case of block cipher are strongly satisfied. Okay, then there are some weaknesses in DES, the design of DES. The very first thing is the key length, as we saw. So for secure cryptographic algorithm, the size of the key should be at least 64-bit. It should not be less than that, but we are having 56-bit key, which is of course not secure, so it is vulnerable to brute force attacks. Okay, so attacker can launch brute force attack, try all the possible combinations and recover the key. Then we have some advances in crypt analysis. So an attacker can use differential crypt analysis and linear crypt analysis and recover the key. So these attacks are possible. Then third drawback is the limited third weakness is the limited block size. So DES has a fixed block size. It can only process 64 bits of data at a time. Now in case if we want to change this number 64 to 128 or any other number, at the same time we cannot do this. So this becomes problematic in many of the in certain applications. Then there is a lack of flexibility. So DES is a fixed algorithm. It has limited flexibility. It does not support different key sizes or modes of operations which are required in cryptographic applications. So there is a lack of flexibility in case of DES. So that's all for this particular session. Thanks for watching.